and this is a metal, you know, like an iron block. Here you'll have less windings, and what will happen is that you have an AC current going through. It'll step the voltage down. So here you might have a very high voltage, whatever's being supplied to your neighborhood. Then for your individual house, it steps it down. It just has less windings going through, and you can remember your alternating current. So it's changing. So now you have a current that's changing, right? And what happens is that this thing gets current based on the induction, the magnetism. The wires aren't touching. That's what's weird. In those transformers, the electric wires don't touch. They just wrap around. You have an iron block, and through induction, right? Everything we just talked about the magnetic fields and all that stuff, it will induce now a current into this, and now you'll get a lower voltage here for your house. Wow. Yeah, and it works that way. So see how important all this is? And it's the ratio of the number of turns. And then, you know, so if you have one voltage here, your voltage 1, and then you want to have your desired voltage 2, well, it's actually based on the number of windings. It's that simple. And you wind this thing around, so you'll have the number of windings in 1, the number of windings in 2. So here, if you have half the number of windings, you'll get half the voltage. Isn't it amazing? And a primary coil is equal to the ratio of the number of turns on the secondary coil to the induced voltage in the secondary coil. And then you can solve for one of those, right? To get your voltage, it would be your voltage times the ratio of your windings, okay? All right, so let's go through. And okay, we're not going to do that. I just want you to know the concepts for this one. So, okay, so this is the last one. So we'll read this one then, since it's the last slide. Wow. Okay. Yeah, so higher voltages are desirable for long distance transmission of electrical power. I talked about that. The higher voltage, the lower the current needed to transmit a given amount of power. Remember, minimizing the current minimizes the heat loss to resistive heating, because wires have resistance. Those high power lines, right, there's wires in it, they have resistance. So remember, your power is equal to your current squared times the resistance. So you want to have your current small, because then you'll have, so you won't lose as much, power just as heat going through the wire. You do that by transmitting very high voltages. So if you have a higher, remember, power is also equal to your voltage times your current. So if you have a smaller current, you want a higher voltage, you get the same power. So they want to transmit thousands and thousands of volts that minimize your resistance losses through the high power lines. Then transformers, you'll step down these very high voltages to lower voltages. Then eventually you'll bring it down, right, into your house. Like typically your washing machine will work at 220 volts, so that comes into your house. And then for the rest of the plugs, in your house, it works at 110. And the way they do that, there's not another transformer. There's a way they just take half of it, the way they connect. We're not going to get into that. So, okay. Now they do sometimes we'll use direct current, because there are actually losses that you will have with AC, because it's going back and forth. There are sort of these inductive losses that you'll have with the atmosphere and stuff. Because even though the atmosphere isn't like an iron bar, if a moist atmosphere, it actually has some resistance to it, but we're not going to get into that. We don't have to worry about that. Anyways, folks, that's enough for today. And that's all. Talk to you later.